All right, so today we're going to start our discussion of filters. And today, particularly, we're going to talk about first order passive filters. And then on Friday and next Monday, we'll talk about second order passive filters. I'm feeling squirrely. I might introduce active filters, but I usually talk about that in detail in circuits 3. So it's not critically important that I talk about it now, literally at all. All right. So let's start with, I hope, a fairly simple and straightforward question. What is the purpose of a filter? In general, what does a filter do? Stop certain things from trying to get through. Absolutely right. So like the filter in your car, you have multiple filters. Like you have an oil filter that's stopping particulate matter from mixing in with the oil and causing buildup and all that kind of stuff in your engine. You have a cabin air filter that's just trying to keep debris out from your cabin air, all of that kind of stuff. So generally speaking, a filter is just something that lets some things pass through, some wanted portion of something, and rejects other things. So in circuits, a filter is something that passes certain frequencies of signals and rejects other frequencies of signals, okay? So there are 4 different general types of filters that we will see. And first, I'm going to introduce the ideal filters, and then I'm going to add on to these graphs what we should actually expect to see, okay? So the ideal filters are also commonly called brick wall filters. So the first response that we might expect to see would be something like this. So on my vertical axis, I'm plotting H as a function of omega. And technically speaking, this is just going to be the magnitude of H. And we'll talk about what H is here in a moment. And then on my horizontal axis, we have omega. Okay. So our first filter might be something like this. So effectively what's happening is up until we hit this frequency right here, which I'm going to call omega C for cutoff frequency, all of our signals are being passed. And then any signal that has a frequency higher than omega C is getting rejected. So over here on the left, we have what's called our pass band. And then over here on the right, we have what's called our stop band, okay? So this is what an ideal low pass filter response would look like. Everything below omega C gets passed, everything beyond omega C gets rejected. This is not what the response of a practical or a real low pass filter will ever look like, okay? So in today's class meeting, we're talking about first order filters, okay? So we have a low pass filter for a real first order low pass filter. It might look something more like this. And so we would actually define our pass band as the frequencies up to a certain point. So have we talked about the units of decibels in this class at all? I know I used it way back at the very beginning for gain of an amplifier. But I don't know if I talked about it past then. Okay. So let me just do this over here as kind of an aside thing. Okay. So a quantity measured in decibels. So let's say that we are talking about voltage gain or something. So voltage gain measured in decibels is just going to be 20 times the log of the output voltage divided by the input voltage, or 10 times the log of the output power over the input power. Son of a bitch. No. Why that thing popped up there. Thank you. Or I would have just kept on trucking. Okay. You may be asking yourself, well, why is one 20 and the other one is 10? It's because of how logarithms work, right? So we know that power is proportional to voltage squared. So that's going to be twice the size of the power, right? Because P is proportional to V squared. Anyway, so we are going to have some maximum value of our response. And for a passive filter, literally the best that we could do would be 0 decibels, which is effectively means we would have a gain of 1. Okay. So the output signal is just as large as the input signal was. Our corner frequency is at negative 3 decibels. Now, chances are literally none of you know this yet, but I'm just going to go ahead and ask it. Does anybody know why negative 3 decibels is used as the corner frequency? What's special about that particular thing? Exactly right. That is the frequency at which half of the power is passed. Okay. So the power rolls off to a factor of 1/2, or the voltage will roll off to a factor of 1 over the square root of 2, representing the exact same thing. That occurs at negative, that change in magnitude is negative 3 decibels. And so whatever frequency that negative 3 dB drop from our maximum value is what the corner frequency of our filter is going to be. And we'll use that here in a little bit. So this is the response of a low pass filter. A first order response might look something like that curve. If we do a higher order filter, it might look something like this. And the more orders we put in our filter, so the more energy storage elements that our filter has, we'll see that response gets steeper and steeper and steeper. So if we were able to have a filter that had an infinite number of energy storage elements, we would finally get that extremely vertical roll-off that our ideal brick wall filter has, but that's not practical because it's going to take up a lot of space and it's going to cost a lot of money. So realistically, we tend to cut things off after 3, 4, 5 energy storage elements. And there are some specialized filter topologies like Chebyshev filters, elliptical filters, Bessel filters, and all of that kind of stuff that we'll talk about in later classes that make lower order filters have a steeper response by allowing signals to resonate some. Isaiah, you were raising your hand. So the corner frequency is the frequency at which the power is reduced by 1/2. So the corner frequency occurs when the amplitude of the signal is -3 decibels lower than the maximum value, right? That's going to depend on where that frequency occurs is going to depend on the circuit elements that we use to establish the filter. And so we'll talk about that for each filter topology when we actually look at a circuit. So right now, all I'm expecting you to understand is the value of -3 decibels is when the signal has lost half of its power, and the frequency at which the signal has lost half of its power is the corner or the cutoff frequency. We all on the same page now? Okay. So this is a response of a low pass filter. Now, let's look at something pretty darn similar. So here's the magnitude of H of omega. And for this guy, we're going to have something like this. So it's going to be low up until we hit our corner frequency. And then it's going to transition to high. Okay. So effectively, all signals having a frequency less than our corner frequency are rejected, and all signals having a frequency above our corner frequency are passed, right? So our stop band is on the left. Same thing, literally interchangeable. So this is the ideal response of a high pass filter. And then obviously for a first order filter, we would see that it doesn't quite go like that. Something more akin to this, and then higher order filters would be steeper and steeper and all of that kind of good stuff, right? So a low pass filter and a high pass filter are the only types of filters that we can make as a first order circuit. Okay, and we'll discuss that in a little bit. But to kind of preload what we're going to be talking about on Friday and Monday, let's go ahead and introduce the response of the other two types of filters that we'll typically see as a passive filter. And so let's look at this guy. So here's the magnitude of H of omega. So we might have something like this, to where we are attenuating signals or rejecting signals up until we hit some frequency. And then we start passing signals again. And then at some other frequency, we start rejecting signals again, right? So this frequency right here, I'm going to call omega low, and it represents the low frequency cutoff or corner. This guy over here, where it goes from passed to reject again, sorry, that says ho, it should say high, my bad. That's our high frequency corner, or our high frequency cutoff. And then exactly in the middle is omega naught. This is the resonant frequency of our circuit, literally the exact same thing as the resonant frequency that we talked about when we were dealing with transient analysis, okay? So this is the frequency at which the impedance of our filter will look purely real, and it also happens to correspond to the frequency that's exactly in between our low frequency cutoff and our high frequency cutoff, okay? This range of frequencies is called the bandwidth of our filter, okay? Realistically, we could have talked about bandwidth for our low pass filter and our high pass filter as well, right? So our low pass filter is just the length of our pass band. For our high pass filter, our bandwidth is effectively infinite because it extends from some point to all frequencies beyond that, right? But in the context of this particular filter, there is a specific band of frequencies over which signals are getting passed, and then everything outside of that, signals are getting attenuated. So over here on the left, we have stop band. Over here on the right, we have a stop band. And then here in the middle, we have our pass band. And so this particular type of filter response is associated with what are called band pass filters. A band pass filter requires at least 2 energy storage elements to achieve, so it can only be done as a second order filter or higher, okay? And then lastly, we have the inverse of a band pass filter. Would be something like this. So we pass signals up until some frequency, we attenuate, and then we start passing again. This frequency is once again omega low. This frequency is omega high. Exactly in the middle, we have omega naught. On the left, we have a pass band. On the right, we have a pass band. And in the middle, we have a stop band. And so this is an example of a band stop, also commonly called a notch filter. And this guy's response is only possible with at least a second order circuit as well. Isaiah, how may I help you?
For the band pass filter, omega naught, the frequency difference looks all
Mhm.
the same thing for this.
Absolutely. Yep. Still the resonant frequency, which by definition is the frequency at which the impedance looks real. So effectively, all of the reactance contributed by the inductance will be exactly canceled out by the negative reactance of the capacitor at this particular frequency. All right, so now let's take a look at a circuit that's used as a filter. Okay, and you guys are going to be just blown away by how complicated this is. So the first circuit that we're going to look at, and I'm not going to tell you what this one is first, we'll give it a name in a little bit, is going to be like this, okay? So here I have some resistance R, and then here I have some capacitance C, and I'm going to represent this capacitance with an impedance of 1 over j omega c, okay? Then over here on the right-hand side, I'm going to have another set of terminals. So on the left-hand side is where I apply my input voltage as a function of frequency. So this is effectively a phasor voltage. And then over here on the right-hand side is where I measure my output voltage, also as a function of frequency. Okay. H of omega is simply the ratio of the output voltage as a function of frequency divided by the input voltage as a function of frequency. So effectively, all H represents is the frequency dependent voltage gain of our system. So it's really nothing that we haven't talked about at length in this class before. It's just now it changes as a function of frequency. Okay. So how are we going to figure out V out effectively as a function of V in for this circuit? I'll give you guys as much time as you need, but it's blown my mind that you haven't answered already. What type of circuit is this? If this was a resistor and this was also a resistor, what would this be? A voltage divider. That's all this is. It is literally a frequency dependent voltage divider. That's it. So our output voltage, V out, and I'm probably going to wind up dropping the as a function of omega bit here in a minute just because I'm lazy and I don't want to keep writing it down. So I'm just giving you fair warning. We're always talking about frequency dependency here. It's just going to be Vn as a function of omega times the impedance of our capacitor. So that's going to look like 1 over j omega c divided by R plus 1 over j omega c. And from this, our transfer function is 1 over j omega c divided by R plus 1 over j omega c. Okay. That's, from an analysis perspective, the simplest form. However, I hate fractions inside my fractions. So in most textbooks, websites, all of that kind of stuff, you'll actually see this expressed as 1 over 1 plus j omega RC, where literally all I have done to get there is multiply by j omega c over j omega c to clear those fractions out. Okay. So this is our frequency dependent transfer function. Okay. Now, it's a little hard to interpret this because it's a complex number. Okay. So what we're going to do next is we are going to split this into a magnitude response and a phase response. Okay. So we have a complex number. If we express it in polar form effectively, we can see how the magnitude varies in frequency and how the phase angle varies in frequency. How the magnitude varies in frequency is the magnitude response. How the phase angle varies with frequency is the phase response, right? So how do I take the magnitude of this guy? What's a complex number? So if I square it and then I square root it, like you're kind of sort of there, but I need to take the, so I square the real part, I square the imaginary part, I add those together, and then I take the square root of that to get the magnitude of a complex number. Unfortunately, in this form, there's not an easily identifiable real part, and there's not an easily identifiable imaginary part. So how are we going to decompose this into a real part and an imaginary part? Hiro, you have a suggestion? So how are you going to split the, you mean split the original fraction or this one that I have right here? This guy? How are you going to split it up? Make it not a fraction. Yeah. Okay. So take the reciprocal, okay. But that still doesn't give me, that gives me a real part of the reciprocal of the transfer function and an imaginary part of the reciprocal of the transfer function, but that's not what we're looking for. Hojun, you've got your hand raised.
The bottom part, top and bottom.
Multiply it by what?
Like 1 plus j omega by 1 plus j omega r.
There we go. I multiply by the complex conjugate in order to get rid of the imaginary part of this thing. So I'm going to take this fraction and I'm going to multiply it by 1 minus j omega RC over 1 minus j omega RC. So that's just a really fancy form of the number 1. But what's going to happen is that my denominator is now going to be a purely real quantity. So if I have a complex number in the numerator, it doesn't matter because I can still just split it up, right? So let's run through that math really quickly here. So hopefully it's pretty darn obvious that 1 times 1 minus j omega RC is just going to look like 1 minus j omega RC in the numerator, okay? So 1 minus j omega RC in the numerator, everything's peachy keen there. 1 times 1 is 1. Then I'm going to have minus j omega RC plus j omega RC. So those parts cancel each other out. And then I have j squared times negative j squared times omega RC quantity squared. Negative j squared is just positive 1. So this is going to look like plus omega RC squared. And now we can split this out. So we're going to have 1 over 1 plus omega RC squared minus j times omega RC divided by 1 plus omega RC squared. Now I have an identifiable real part and an identifiable imaginary part so that I can apply our just basic rule for finding the magnitude of a complex number. So we'll do exactly that, right? So the magnitude of h as a function of omega is going to be the square root of the real part squared. So that's going to look like 1 over 1 plus omega RC quantity squared. Then I square that whole fraction plus negative omega RC over 1 plus omega RC quantity squared. Square this whole thing. Continue my square root sign. Okay. So let's keep on trucking with this. So in my denominator, I hope it's fairly obvious that I am going to have 1 plus omega RC squared, right? I have a common denominator on both sides, so I can just lump all that stuff together. In my numerator, I have 1 plus omega RC squared. So this guy right here winds up canceling one of those powers. And what I'm left with is 1 divided by the square root of 1 plus omega RC squared. So this is what my magnitude response is going to look like. Okay. So now we can figure out what type of filter this is by evaluating this expression at a couple of key frequencies, okay? So what will be the value of our magnitude response at omega is equal to 0? 1, right? Because we're going to have 1 over the square root of 1 plus 0. So 1 over the square root of 1 is just 1. So how we are interpreting this is that very low frequencies, DC, all of our input signal is passed to the output. That's what that ratio is, right? V out over V in equals 1 means all of our input signal made it to the output. At extremely high frequencies, omega is approaching infinity. What is our magnitude response going to look like? 0, because we're going to have 1 over the square root of infinity squared is looking like 1 over infinity or 0. So we pass very low frequencies. We attenuate very high frequencies. What type of filter is this? A low pass filter. Now, let's figure out what our corner frequency is, okay? So our corner frequency is defined such that, so at omega c, the magnitude of h of omega will be equal to 1 over the square root of 2. This is our half power frequency. Because we're dealing with voltages, that's why it's going to look like 1 over root 2 instead of 1/2 specifically. Okay, if we multiplied this by itself, it would literally come out to be 1/2, which is our half power frequency. Okay, so how do we make 1 over the square root of 1 plus omega RC quantity squared equal to the square root of 1/2? How does that happen? At what frequency? Well, we've already got a 1 in the numerator on both sides, so that's pretty awesome. We already have a square root in the denominator on both sides, so that's pretty great. Effectively, all we need to do is make 1 plus omega RC squared look like 2. Or omega RC needs to look like 2 minus 1 is equal to what? So our corner frequency is what? There we go. 1 over RC. That will be our half power frequency for this first order RC low pass filter. Absolutely right. Okay. All righty. So we know what type of filter it is. We know where the cutoff or corner frequency is. So now we just have to figure out what the hell the phase angle is doing. Okay. So that we have a total picture of how our signal changes as it goes from the input to the output of our system. Okay. So we can do this really quickly. Theta as a function of omega, and I'm literally just using a definition that we developed in circuits 1 for finding the angle of a complex number, is the inverse tangent of the imaginary part of our complex number. So this would be the imaginary part of h of omega divided by the real part of h of omega. Okay. So that's going to be the inverse tangent of our imaginary part was negative omega RC divided by 1 plus omega RC quantity squared. All of this over positive 1 over 1 plus omega RC quantity squared. So we have a common denominator for both of those fractions. So they're going to cancel each other out. And so now this is just going to look like the inverse tangent of negative omega RC. And technically we would take that negative, or we can take that negative sign out of the omega RC and just put it out in front, because the tangent of, or excuse me, the arctangent of negative x is just negative the arctangent of x. But we can leave it in, we can take it out, whatever the hell we feel like. Okay. So we now know how the phase angle changes as a function of frequency, as well as how the magnitude changes as a function of frequency. So we have a complete picture of the frequency response of this filter. Okay. So before we move on to another circuit, I want to get LT Spice out and I want to show you how to simulate one of these. Let's do something wildly easy. And let's say that R and C are just 1. Okay. So this is what we would call a normalized filter, and we'll talk way more about that in circuit 3. Effectively, what we're going to find out is that we can effectively look at any filter circuit with all of the components having a value of 1 to figure out how it works, and then we can scale it in frequency using a couple of equations and all that kind of stuff that we'll learn later on to be able to handle any component values. All right, so let's make a new circuit. It's not remotely what I wanted. I need a voltage source. I need a resistor. And a capacitor. Let's wire things up. I'm just going to give myself a stub of wire over here. Stub of wire over here. And a little stub of wire down here. I'm going to put my ground down here at the bottom. So I already said we're going to use the resistor value of 1 and a capacitor value of 1. So now let's talk about how we're going to set up our voltage source. So I'm right-clicking my voltage source and I'm going to the Advanced tab and I'm ignoring literally everything on the left. That has nothing to do with what we're about to do. Over here on the right-hand side, I'm going to go into the area where it says Small Signal AC Analysis. I'm going to choose my AC amplitude as 1, and I'm going to leave everything else blank. So effectively, what my voltage source is it's a voltage source with a phasor representation of 1 angle 0 degrees for all frequencies. The reason why I'm choosing this particular value to be my input voltage is because now whatever I measure as my output voltage is exactly our transfer function, because we would just divide that by 1 angle 0 degrees. Okay. I'm going to call the voltage at this node V out, And now I'm going to simulate this thing. So I'm going into my simulation, edit simulation command option, and I'm clicking on the AC analysis tab. I think this is the first time we've used it in this class, and I'm going to do a decade sweep. So what that means is effectively I'm going to get a logarithmic plot, okay? On the vertical axis, I'm going to get my frequency response measured in decibels. And on the horizontal axis, I'm going to have frequency measured in hertz, but it's going to go from like a millihertz to a hertz to a kilohertz to a megahertz, et cetera, et cetera, et cetera. So that's the standard form of a frequency response plot, is that the frequency is changed logarithmically and the output is effectively in decibels. So it's also effectively a logarithmic function. Just for the sake of argument, I'm going to put in 1,000 points per decade. For this simple of a circuit, this is really, really overkill. But for one of your design problems that you're going to have to do using filters, something like 1,000 points per decade or maybe even more would be appropriate. The more points you put per decade, effectively, the smoother the graph is going to look. Like, so let's look at it with 1,000 points per decade, and then let's look at it with, like, say 10 points per decade in a moment and see it's going to look all janky. I'm going to start my frequency at, let's say, just for the sake of argument, a microhertz. So that means one cycle every million seconds. And I'm going to stop it at a megahertz. So let's put 1U and then 1. And for megahertz, I have to type MEG. If I just do capital M, it interprets that in the exact same way as a lowercase m, and so it would call it a millihertz, not a megahertz. So to get a mega anything, you type MEG, and I just use a capital letter because I'm used to doing it. So this is what our SPICE code for running the simulation is going to look like. And now I'm going to run my simulation. So notice on my plot, it's going from a microhertz, then 10, then 100, then a millihertz, et cetera, et cetera, et cetera. So that's what a decade sweep looks like. Every major tick mark is 10 times larger than the one previous. Okay. And the distance between 10 millihertz to 100 millihertz or 100 millihertz to 1 hertz, et cetera, is what's called a decade. So it's just an increase by a factor of 10. Now I'm going to click the output voltage node, and I'm going to change the limits here very slightly. So I want my top to be at positive 10 decibels. That's just so that that top line is not at the very top of the graph, so we can really see what's going on there. So this looks like a low pass filter response. The heavy line is the magnitude response, and the dashed line is the phase response. So here we can see that up until somewhere in the ballpark of 100 millihertz, practically everything is getting passed. And then somewhere in the ballpark of 100 millihertz, it starts to roll off. And it rolls off at a slope of negative 20 decibels per decade, right? So if we look at what's going on here, let me just prove this to you really quickly. So let's look at what's going on at, where's my cursor thingy? There we go. At 10 hertz, or as close to we can get it as possible. Okay. So at 10 hertz, we have a magnitude of negative 36 decibels, thereabout. At 100 hertz, it should be negative 56 decibels. I left clicked on the V out label up here to give myself a cursor. So for a first order filter like this, we are going to see a roll off of -20 decibels per decade for a low pass filter, and we're actually going to see an increase of 20 decibels per decade for the high pass filter. For second order filters, and I don't want to go too deep into the weeds on this, but effectively, if our poles are at the same location, we'll see 40 decibels per decade. If we have a third order filter with the poles at the same location, it would look like 60 decibels per decade, et cetera, et cetera, et cetera. So like every energy storage element is going to make our slope increase by 20 dB per decade. All right, so let's figure out what our -3 dB cutoff frequency is, right? So if I go over here to the left-hand side of the graph, it's telling me that my magnitude is -734.296 nanodecibels. That's 0, right? That is an incredibly small number. So we have 0 dB when we're in the pass band. And so now, if I can find my cursor, there we go. I'm literally just looking for what frequency my magnitude is -3 dB at. So it looks like 159.427 millihertz or so. Okay. Does this agree with what the math tells us? So if I put in an R value of 1 and a C value of 1, what should my cutoff frequency be? One radian per second. But our graph is in hertz, right? So how do we go from angular frequency to linear frequency? Indeed, we do have to convert it, smartass. How do we convert it?
60 pi.
60 pi, sweet lord. There's definitely something with pi. 2 pi, yes. There are 2 pi radians in every cycle, right? So a hertz is effectively per cycle. An angular frequency is radians per second, whereas linear frequency is measured per second. So it's a 2 pi conversion factor. So if we divide omega c by 2 pi, 1 over 2 pi, what would we get? You've got calculators. Give me a damn decimal.
My calculator won't load.
0.159. I'll be damned. 0.159. So like, I don't know, 159 millihertz? Yeah. So this is agreeing with our math exactly. We just have to be smart enough to realize that the math we do is in radians per second, and the plots we're going to get is in linear frequency of just per second or in hertz, right? So 159 millihertz effectively exactly matches what our expected cutoff frequency is based on the math. Isaiah, you're raising your hand again.
On the big bold line, I can't see it at all.
Right now, let me find it somewhere in this ballpark. I wonder if there's a way in settings. I'm sure there is actually. Damn it, stop randomly. Hope I didn't just close out Zoom. I don't think I
Why
did.
did your like open slice the grid is white, but on everyone else's spot?
Because I set it to white so that, yeah. So if I go to tools and I go to, let's go to color preferences. So if I literally click on to edit my background color, right now it's 255 red, 255 green, 255 blue. Yours is probably set to 0 red, 0 green, 0 blue, or black. but I like having it white. Because when I use this to put add plots and stuff into files and have to print them, it doesn't waste a shit ton of ink, and then you can't actually see the waveform at all. So this is how I have it set. Okay, now I can change the default color of my traces and all of that kind of stuff, which is not remotely what I'm looking for. Edit trace color, no. And we're just killing time. I'll try to figure out if there's a way to change the color of my cursor so that it's easier to see where it's at. But I'm literally just kind of looking around until my cursor turns into a 1, and then that's where I know where it was. So just going back to where we were. All I'm doing is just looking at that plot on the, or not the plot, the kind of table thing on the bottom. And I'm trying to get the magnitude as close as possible to -3 decibels. When I did that, I can see that the associated frequency is 159 millihertz. Okay. So this is a low pass filter utilizing a capacitor. Okay. Any questions before we go back to note related stuff? All right.
Is the bank line what we drew here?
Let me go back to the notes. Tell me what you're talking about.
On the first graph we drew. The first graphs we drew there.
Like this kind of stuff. So on LT Spice, the bold line, let me change it to a different color because that green may be difficult to see. Let's put it in blue. Hit okay. So the bold line is the magnitude response, which is just like the line I have in blue here. The dashed line is how the phase angle changes. So the left axis is what's going on with the bold line, and the right axis is what's going on with the dashed line, right? So effectively, we can see that for very low frequencies, our gain of our system is 0 decibels, or effectively 1. And then once we go beyond that cutoff frequency, it begins falling off at a rate of -20 decibels per decade. So like down here at this point, which looks to be about probably 1.6 kilohertz or so, just ballparking here, our gain is -100 decibels. Actually, let me go to where it's -120. So that would be at roughly 160 kilohertz. That means that at that frequency, our signal is literally 1,000,000 times smaller than what it started as. So if we put 1 volt in, we would get a microvolt out at that particular frequency. Okay. We can also see, if we look at this graph, that for very low frequencies, the phase angle of our signal is unchanged. It's not until we start getting to pretty much within a decibel, or excuse me, within a decade of our corner frequency where our phase angle starts to change. At exactly our corner frequency, our phase angle is -45 degrees. And then about a decade beyond our corner frequency, we see that our phase angle settles to -90 degrees, okay? Which is effectively what we would expect for a first order response. So let's talk about that just really quickly. Why does this circuit work as a filter? This is just a voltage divider, right? Why is it passing some signals and rejecting some signals? So it doesn't have anything to do with the capacitor voltage can't change abruptly, but it very much has to do with the fact that there's a capacitor in the circuit, right? The impedance of a capacitor changes as a function of frequency. At very low frequencies, a capacitor looks like an open circuit, so effectively an infinitely large impedance. Well, at very high frequencies, the capacitor looks like a short circuit. So that's why our output voltage trends towards zero as the frequency gets higher, because we're taking the voltage drop over something that's looking more and more like a short circuit as our frequency increases. Okay. So without going into a huge amount of detail here, because I think I have a homework for this. Let's say that I had this filter circuit. So I have an impedance here of j omega L. I have a resistor here with an impedance of R. Here's my input voltage. Here's my output voltage. Use your intuition and knowledge of circuits and tell me what type of filter you think this is going to be. So Walker, when you say it's the completely opposite of the capacitor, do you mean that you think this is going to be a high pass filter? Because the capacitor circuit we just had was a low pass filter. That is what you mean. Okay. So I don't think you're correct. I might be misremembering here. I think it's going to be a low pass filter. So let's talk about why I think it's going to be a low pass filter. What does the impedance of the inductor look like at very low frequencies? A short circuit. So effectively, at very low frequencies, our input voltage is connected in parallel with that resistor R, and then we're measuring the output voltage as the voltage drop across that resistor R. So for very low frequencies, V out should effectively be V in. At high frequencies, what does the impedance of our inductor look like? Trending towards an open circuit, which means no current can flow through that inductor, which means there will be no voltage drop across our resistor, which means our output voltage will trend towards zero. So it will be a low pass filter. So we can make low pass filters, and as we'll see in a moment, high pass filters with either a capacitor or an inductor, just depending on where we place them, right? So, like I said, we went through this. This is going to wind up being a low pass filter. At some point in the near future, I'll ask you guys to figure out what its magnitude and phase response is and all of that kind of stuff. Process will be rather similar to what we did a moment ago, right? So now let's look at this guy. So it's our first filter, except that I'm swapping the position of the capacitor and the resistor. We've got less than 10 minutes left to do this, so I'll go through it relatively quickly, but I don't think it'll be too taxing. So by process of elimination, And what I mean by that is we know that a first order filter can only be a high pass filter or a low pass filter. We already know that the other circuit was the low pass filter. This is probably the high pass filter, right? So at very low frequencies, our capacitor is going to look like an open circuit, which is able to pass through the resistor R, so no voltage drop occurs over resistor R. Very high frequencies, our capacitor is going to look more and more like a short circuit, which means our input voltage is directly in parallel with our resistor, so our output voltage is effectively the same thing as our input voltage, right? So we should be able to pretty easily infer that this is going to behave like a high pass filter. All right, so what should our transfer function look like? I'm not going to bother finding V out as a function of V in. We should be able to just do this directly because it's just going to be the ratio part of the voltage divider relationship, right? So here, this would look like R divided by R plus 1 over J omega C. Anybody have a beef with that? If I multiply through by J omega C over J omega C, this is going to look like J omega RC divided by 1 plus J omega RC. I'm going to multiply this by 1 minus J omega RC over 1 minus J omega RC. And what I wind up getting is negative J squared, so that's going to be positive 1, omega RC quantity squared over 1 plus omega RC quantity squared. And then I have plus J times omega RC over 1 plus omega RC quantity squared. If I did that mental math correctly, let me double check that just really quick. So J times negative J looks like positive 1. Omega RC times omega RC is omega RC squared. So that's where that bit came from. J omega RC times 1 is just J omega RC. Yep, pretty hard to screw that up. Just wanted to double check. From here, our magnitude response is going to be the square root of our real part squared. So omega RC squared over 1 plus omega RC squared. Square this whole thing. Plus omega RC over 1 plus omega RC squared. Square this whole thing. So in my denominator, I hopefully very obviously have 1 plus omega RC quantity squared, and then that whole thing squared. And then in my numerator, I have omega RC to the 4th power plus omega RC to the 2nd power. So I'm going to choose to express that as omega RC squared times 1 plus omega RC squared. Sorry, that bracket on the end isn't necessary. So everybody okay with how that numerator is going to look like omega RC to the 4th power plus omega RC to the 2nd power? No witchcraft or anything going on, just hopefully very simple algebra. We can then see that this part right here winds up canceling one of our powers here, giving us a frequency response of, magnitude response of omega RC divided by the square root of 1 plus omega RC squared. So let's verify that this works as a high pass filter. What is our magnitude response look like when our frequency is very low? To me, it looks like 0/1, which is 0. What does it look like when our frequency is very, very high? Infinity over the square root of infinity squared, or 1. So low frequencies get stopped or attenuated, high frequencies get passed. Our presumption that this is a high pass filter is obviously correct. Now we need to figure out what our cutoff frequency is, right? So how do we make omega RC divided by 1 plus omega RC quantity squared look like 1 over the square root of 2? Well, what if we multiplied this guy right here by 1 over omega RC over 1 over RC? That makes our numerator look like 1. And then I'm going to have the square root of 1 over omega RC squared plus omega RC over omega RC squared, or 1 over the square root of 1 plus 1 over omega RC squared, right? How does that denominator look like the square root of 2? Over RC again. So our cutoff frequency for any first order filter using a capacitor is always just going to be 1 over RC. Doesn't matter if it's a low pass filter or a high pass filter. Okay. So we know what our magnitude response is. We know what our cutoff frequency is. We've got 1 minute to do our phase response. So let's crank that out really quickly. So theta as a function of omega is the arctangent of the imaginary part. So the imaginary part of this guy is omega RC. I know that if I look up here just really quickly, the real part has a denominator and the imaginary part has the exact same denominator. So when I do those ratios, those parts are going to cancel out. So I'm not going to bother writing it down anymore because it's a pain in the ass. Down here, I'll have omega RC quantity squared. Very obviously, this guy kills that guy. And so we have a phase response of the inverse tangent of 1 over omega RC. So if we were to simulate this circuit, it would effectively have this exact response, but flipped upside down. Both the magnitude and the phase. So we would see the phase goes from 0 to positive 90 degrees as frequency increases, and we would see that we go from very low, like, let me just draw it just really quickly. Looks something like this, and then, so this would be H of omega, where up here, this is 0 dB. And then for our phase response, which I'm going to do in gray, it would be something like this, where this is 0 degrees and this is positive 90 degrees. Okay. All right, went 1 minute long, so I'm done.